All right, so let's just go through each of the questions really quick. A blogging website allows users to post messages and to comment on other messages that have been posted. When a user posts a message, the message itself is considered data. In addition to the data, the site stores the following metadata: the time the message was posted, the name of the user who posted it, and the names of any users who comment on the message and the times those comments were made. So which of the following goals would be more useful to analyze the metadata instead of the data? Is analyzing the time of day that the site is most active going to come from metadata or data here? That one's going to come from our metadata because that time was part of our metadata. So seems like a pretty good front runner. Determining the topics that many users are talking about. Topics are part of the actual message. That's part of our data. So not that one. Determine what words are most commonly capitalized in comments. Once again, the comment data is our data, not our metadata. And the least common punctuation also contained in the data rather than the metadata. So there's our first answer. A blogging website allows users to post messages and to comment on other messages that have been posted. When a user posts a message, this is the same prompt. Which of the following questions could not be answered using only the data and metadata collected? Which users post messages most frequently? What time of day is the site most active? Which posts from a particular user have received the greatest number of comments? And in which country is the site most active? So I think the only piece of information that we don't have here is that country data. It's not included in the comment unless they specifically comment that, but unless every single person is commenting, "I'm from this place," that's not information that we have access to, and it's not in any of our metadata. So that is our answer. That is the question we can't answer using only this data we have specified here. All right, a chat website allows users to post messages. The message is our data, and we store the time the message was posted and the city from which the message was posted as our metadata. So what could we not answer using this data and metadata? What topics are most frequently posted about in a particular city? When is a particular city most active? Which users post messages most frequently? And what topics are most frequently posted about during a particular time period? Which of these is not possible? So let's go through and eliminate. Which topics are most frequently posted about in a particular city? So we know the topics because that's in our data. We know a city, we've got that, and we can just kind of count frequency of posts. So that seems like it is possible. When is a particular city most active on the site? We have time, we have city, both of those seem good. Which users post messages most frequently? Are we keeping track of users here? All we're keeping track of is the actual comment, when and where it was posted from. So we don't have access to users, and topics most frequently posted about during a particular time period. It's very similar to our first question, except for using our other piece of metadata. So we don't have access to this user information because that's not the metadata we're storing. All right, biologists are researching the migration patterns of birds. They have attached tracking collars to several wild birds. For each bird, the following geolocation data is collected at frequent intervals. Time, date, and location. Which of the following questions could not be answered using only this data? How far did it travel in 1 year? Does it travel in groups with other tracked birds or separately? Does the bird's diet change? Or in which months did the bird travel the farthest? Since all we have is time, date, and location, we don't know what it's eating. There's our answer. Same exact question. We know the time, date, and location of the bird. What could we answer using only this data? How many new birds were born? In what month do birds tend to travel the farthest? do the migration patterns of birds vary according to the weather? And what is the most common cause of death in this group of birds? Which one could be answered using this data? Do we have any way to track birds? I don't think so. We're not tracking new babies. They don't come out of the egg with a tracker on their neck, so you can't track birds. Do we track the weather? Nope. All we have is time, date, and location. We can maybe extrapolate our weather based on that, but I would take a lot of extra work. And most common cause of death, we're not tracking deaths either. So we do have time and date and location. So we know how far they're moving on various different time periods. So we know this information. All right, computers are often used to search through large sets of data to find useful patterns in this data. Which of the following tasks is an example where searching for patterns is needed to produce useful information? A, high school searching over student GPA, so identify the student with the highest GPA. Is there a pattern there? No, we're just looking for a single instance. So not that one. A grocery store searching over its inventory to determine which items are running low. That's just finding counts. So maybe, but probably not. A music application searching over a user's library to determine if a particular song exists. Definitely not finding a pattern there. Or an online retail store analyzing customers' viewing habits to suggest other products based on the purchasing history of other customers. That one, we are looking at other people. We are analyzing our own habits. So this, we're looking for patterns and trying to establish something. So that one seems like it's the correct answer. All right, streaming service sites stores information about the song streamed by its users. We are summarized and stored in a publicly available database. Day and date each song we listen to, title of the song, cities where users listen to the song, and number of times each song was listened to in a given city. So if we look at this database, here's a sample little portion of it, sorted by date and song title. Which can we not determine based on this information? The city in which a particular song was listened to the greatest number of times, the number of songs listened to by a particular user in a particular day, the song that is most listened to in a particular city, or the total number of cities in which a particular song was listened to. So we have our city data, so we can do all of those. We don't have any individual user data here. All we have is overall city data, so we can't track the number listened to by a single user. All right, a music streaming service that stores information about the songs streamed by its user. Every time a song is streamed, the following information is stored in a database: title, artist, and date and time song was streamed. What can we not determine? The most popular artist in a given day, most popular song in a given day, time of day the site is the most active, or the most popular artist in a given city. Once again, find the piece of information we don't have, and that's our city. So there we go. Streaming service stores information, artist, title of the song, artist of the song, date and time of the stream, name of the user streaming the song. What can we not determine? Particular user's top 10 most played songs of all time, particular artist's most popular song of all time, date that a song reached its peak popularity, or a popular music genre played by a particular user. Once again, find the information we don't have, and that's our genre. We don't have any genre information here. We just know what the name of the songs are. So we could maybe extrapolate, but that's not data that we have available in the database. A music streaming service stores information about the song streamed by its users. Every time a song is streamed, the following information is stored in a database: title, artist, date and time, and city. What can we not determine? Particular user's top played song of all time, in which city an artist is most popular, which city has the most songs streamed in a particular day, or the total number of songs streamed on the site in a particular hour. So what information do we not have? Once again, we don't have particular users. A lot of these questions are looking a little similar. A large data set contains information about all students in all colleges across the United States. It contains the following information about each student: gender, state, where they attend college, their grade point average, and their major. What could we answer by analyzing only information in this data set? Which college has the highest number of female computer science majors? How many states have computer science as the most common major for female students? Do students attending college in the United States tend to have a higher grade point average than students in other countries? Or which state has the highest graduation rate for computer science majors? Do we know what other countries look like? No, so other countries disqualifies that one. Our GPA doesn't necessarily tell us our graduation rate, so I think we have that information. And then we don't have any specific college information either, so we don't know which specific college has the highest number of female CS majors. So all we know is how many states have CS as the most common major for female students. A search engine has a trend tracking feature that provides information on how popular a search term is. The data can be filtered by geographic region, date, and search term. Which of the following questions is least likely to be answerable using this feature? In what month does swimming pool receive the most searches? Which region of the country has the greatest number of people searching for a certain musical artist? What region of the country has the greatest population of a particular animal? And when are flights to Hawaii most often purchased? So I feel like we could definitely track searches for swimming pool. So that one is definitely not in the running for least likely. In which region of the country has the greatest number of people searching for a certain musical artist? We're including searching here as well. Which region of the country has the highest population of a particular animal? I don't see any place for animal populations here. And when are flights to Hawaii most often purchased? People are probably doing some kind of a search for Hawaii flights, so that one seems feasible. So we don't have anything about animal populations in our data here. An online retailer that sells clothing maintains a database containing item ID number, clothing type, price, size, color, and how many are available. What can we determine? Which item is most expensive? Which color is most popular among teens? What number of shirts are sold in a particular day? And which sizes are more popular among women than men? I don't see anything about popularity, so neither of these. And we're not keeping track of flow. We're not keeping track of things that are being added or subtracted from the database. So we're not tracking how many things got sold. All we can determine is which of our things has the highest price tag. With that same set of things, what cannot be determined? Which items are unavailable? What colors of shirts are only available in large? What shirt has been purchased the most? Or what item is purchased the most? And what clothing type is on average the cheapest? Once again, we don't have any kind of flow data. We don't know what things are being added or subtracted, or we're not tracking our quantities going up or down. So we don't know what has been purchased the most. And our last question: when a cellular telephone sends a text message, a cell carrier encodes the text message and transmits the message to a receiving cellular telephone. Encoded message is the data of the transmission. In addition to transmitting the data, the carrier also stores metadata. The metadata includes the time it was sent, the phone number of the sender and receiver. Which of the following goals would it be more useful to computationally analyze the metadata instead of the data? Number of texts sent next month, determine the most frequently used emojis in text messages, determine if two phones have been in contact in the last week. So if we are only looking at the metadata, do we know which emojis are being used? No, we do not. So 2 is disqualified. So we can get rid of that answer and that answer. If we know what time a message was sent, if we're keeping track of that, we might be able to guess, based on the number we sent this month, how many are going to be sent next month. So that seems feasible. And can we determine if 2 phones have been in contact? If we have our metadata storing our sender and receiver, we can definitely track that. So 1 and 3 are both feasible there. Okay. Second set of questions. A byte is made of 8 bits. You have a programming language that uses 1 byte to represent characters, and you are modifying your language to use 2 bytes to represent characters. How many more characters can you represent? So we have 8 bits, and we're increasing to 16 bits. What was our equation for finding the difference? To the power of y minus x. So 16 minus 8 times as many. So to the 8 times as many characters is our answer. Same kind of problem. We have 32 and 128 bits. 128 minus 32 gives us 96. We have 2 to the power of 96 times as many addresses can be used. Very similar question. We have n bits. We add 1 bit. We can store 2 times the number of values. A video watching website previously used 32-bit integers to store the number of views for each video, but a video that had watched billions of times hit the maximum value. What is it called when this maximum is exceeded? Is it overflow, maximum, kilobyte, or viewing error? Which of these makes the most sense? I don't know if we actually talked about this during last time. Overflow definitely makes the most sense out of these words. So yes, this is an overflow kind of an error. And then once again, if we have 1 hexadecimal digit, how many more values can we represent? Kind of disregard this question because hex is not going to be on the AP exam. But if I have 1 hexadecimal digit that goes anywhere between 0 and 16, binary is going to go anywhere between 0 and 1. So we got 2 values versus 16 values. So we have 8 times as many. All right, and our final quiz was about encoding. So with this ASCII table, what letter is represented by this binary sequence? 1, 0, 1, 0, 0, 0, 1. So let's look at our values. 1, 2, 4, 8, 16, 32, 64. So we're going to add 64 plus 16 plus 1. That equals 81. Does that seem right? Yeah. So 81, if we look at our table, 81 gives us the letter Q. So Q is our answer there. Question 2, same style of question, except we are going to have a different binary sequence. So with the binary sequence 1, 0, 0, 0, 0, 1, 1, we're adding 64 plus 2 plus 1, 64, 65, 66, 67, gives us the letter C. All right, yet another one of these. New sequence. We have 1, 0, 0, 1, 1, 1, 0. So 64 plus 8 plus 4 plus 2, 74, 78. So we got 78 from this. We look at our chart. That gives us the letter N. So these should hopefully be fairly straightforward. And our last sequence of questions, I don't think you're going to see anything like this on the exam because, or you might see a comparison between binary and decimal, but you don't have to worry about hex on the exam. So let's look through these and see what we get, but you don't have to do this exact kind of problem on the exam. You're not going to work with hex. So we want to order from least to greatest. I think the easiest way to accomplish this is just to convert everything to decimal and compare there. So 1, 1, 1, 0, 0 is equal to 2, 4, 8, 16. 16 plus 8 plus 4 equals 28. So that's definitely smaller than 30. So we know that binary is going to come before decimal. So we can eliminate that one. Binary came after decimal there. And 1D, this is 16 to the 0. This is 16 to the 1. So we have 16 plus A equals 10, B equals 11, C equals 12, D equals 13. So 16 plus 13 is going to equal 29. So we're going to go binary, hex, and then decimal. Binary, hexadecimal, decimal is our sequence, smallest to largest. All right, another one of those. 1, 0, 0, 1, 0, 0, 1. 8, 16, 32, 64. So that is going to equal 64 plus 8 plus 1, 73. And then 4E, 4 times 16 plus E times 1. 16 times 4 is 64, thank you. And then E, A, B, C, D, E, 10, 11, 12, 13, 14. 64 plus 14, 78. So our decimal is now smallest, then binary, then hex. Decimal, binary, hex. All right, digital images can be represented and stored by the red, green, and blue values of each individual pixel in the image. If you're manipulating a digital image and overwriting the image of that is not what a conditional sentence looks like. If you are manipulating a digital image and overwriting the original image, I assume that's supposed to be a comma, not a period. Which of the following describes a lossless transformation of the digital image? Swapping the values between R and G to turn the green parts of the image red and the red parts green. Set the blue value of each pixel to 0, so it makes the blue parts of the image go away. Compressing the image by decreasing the number of bits per RGB value by 1, or creating a grayscale image by averaging the RGB for each pixel and displaying it as a shade of gray, ranging from white to black. So in which of these are we not losing any data? Let's look at each of these. If we're just swapping R and G, are we going to lose that data? We're just doing a swap. Now, so the data is maintained. If we set the value of each blue pixel to 0, we're definitely losing whatever blue was there. So that's lossy. Compressing the image by decreasing the number of bits, that's definitely going to be lossy. And averaging the RGB, we're losing the original values for the red, green, and blue by doing this average. So all three of those perform some loss, giving us that one as our correct answer. That all track? Alrighty. No, I need to mouse. So today we are going to be doing a couple of other quizzes. These ones are once again just practicing programming on the AP exam. So let me make sure that those are unlocked for you now. This is quizzes fill in the missing code and programming style. So 1.2.6 and 1.2.7 are now available. We'll work on those till the end of class, and then we can recap those beginning of next class. So I will stop our recording here.